You know, have you ever actually stopped to wonder why a tiny water strider can literally walk across the surface of a pond without sinking? Or why, if you accidentally knock over a glass of wine, the liquid instantly races up a paper towel, completely defying gravity? Well, in this explainer, we are going to trace these really fascinating everyday phenomena right back to their source. We're talking about the invisible, microscopic forces that dictate exactly how matter behaves.
Here's our roadmap for today. We're going to start off with those invisible forces, explore some cool liquid properties, and then examine what I like to call the great phase escape. After that, we'll tie the whole thing together with heat, energy, and these master maps known as phase diagrams.
All right, part one, the invisible molecular forces. Let's get into the hidden mechanics of matter. To really grasp how matter behaves, you kind of have to imagine molecules like cars driving on a highway. If intermolecular forces are the heavy-duty welds and bolts holding a single car together, intermolecular forces, or IMFs, are more like magnetic bumpers. They cause those completely separate cars to attract and stick to one another as they drive. And the energy difference between the two is staggering. Just to break the actual chemical bonds, those internal intramolecular welds between the hydrogen and chlorine atoms in 1 mole of hydrogen chloride, it takes a massive 430 kilojoules of energy. But to simply overcome the intermolecular magnetic bumpers, meaning just separating liquid HCl molecules to turn them into a gas, it only takes about 17 kilojoules. So it requires roughly 25 times more energy to break a molecule's internal structure than it does to just pull separate molecules apart from one another. Now, there are 3 main types of these attractive forces that determine a substance's physical state. First up, we have dispersion forces. These are relatively weak, temporary attractions that just happen when molecules get super close to each other. Interestingly enough, heavier and larger molecules actually have stronger dispersion forces. That's exactly why a lighter halogen, like fluorine, is a gas at room temperature, but a heavier one, like iodine, is a solid. Next, we've got dipole-dipole attractions. These happen in polar molecules that have permanent partial charges. It's very much like magnets locking their positive and negative ends together. And finally, we have the absolute MVP of molecular attraction, hydrogen bonding. This is an exceptionally strong type of dipole-dipole attraction that kicks in when hydrogen is bonded to a highly electronegative atom, like fluorine, oxygen, or nitrogen. When you picture a water molecule, imagine the oxygen pulling electrons away from the hydrogen. What happens is these highly concentrated partial charges form, making the molecules incredibly sticky. They end up creating this strong, interconnected network of hydrogen bonds. Now, keep in mind, these aren't full-on covalent bonds. They're only about 5 to 10% as strong. But compared to other intermolecular forces, they are incredibly powerful, and they completely transform the properties of the liquid. Moving on to part 2, everyday liquid properties. We're talking viscosity, surface tension, and capillary action. Okay, so now that we understand these microscopic sticky forces, let's look at how they actually govern the macroscopic world, the liquids we interact with every single day. Think about pouring a simple glass of water, and then compare that to squeezing honey onto a biscuit or pouring motor oil into a car. Water flows instantly, right? Honey and motor oil definitely do not. This resistance to flow is what we call viscosity, and it all comes right back to our molecular cars. Structurally complex molecules with strong intermolecular forces practically lock arms with each other, making it incredibly difficult for them to slide past one another. To really put the scale of this effect into perspective, let's talk numbers. Water has a viscosity of just under 1 millipascal second. Ethanol is slightly higher, but then jump down to motor oil, and suddenly we're looking at 50 to 500. And honey? Honey has a staggering viscosity of roughly 2,000 to 10,000. That massive numerical jump beautifully illustrates how molecular size, complex shapes, and those strong intermolecular forces just slam the brakes on a liquid's ability to flow smoothly. And hey, this brings us right back to that spilled wine from earlier. When a liquid climbs up a porous paper towel, literally working against the pull of gravity, we're witnessing capillary action. It's actually the exact same mechanism that plants use to draw water all the way from their roots up into their highest stems. It's even the reason your eyes stay lubricated with tears. Capillary action is driven by this really fascinating tug-of-war between 2 distinct types of forces, cohesive and adhesive. Cohesive forces are simply the attractions between identical molecules. Think of it as water molecules holding hands with other water molecules. Adhesive forces, on the other hand, are the attractions between 2 different molecules, like water molecules clinging to the cellulose fibers in a paper towel or gripping the glass walls of a tube. So, when the adhesive forces pulling the liquid up the surface, combined with the cohesive forces holding the liquid together, are stronger than gravity itself, the liquid rises. Okay, Section 3, the Great Phase Escape, Vaporization and Dynamic Equilibrium. So, how do molecules eventually break apart? Well, imagine a liquid sitting inside of a closed container. At any given temperature, the molecules have varying levels of kinetic energy. The ones with enough energy right at the surface can actually break their intermolecular bonds and escape into the gas phase. That's vaporization. But because the container is closed, those new gas molecules bounce around. And inevitably, some collide with the surface and re-enter the liquid. That's condensation. Give it enough time, and these two reciprocal processes will eventually happen at the exact same rate. This is what we call a dynamic equilibrium. And the pressure that the gas exerts at this specific balancing point, that is the liquid's vapor pressure. Now here is a really cool real-world puzzle for you. Normally, we're taught that water boils at a nice, even 100 degrees Celsius. But in a place like Leadville, Colorado, which sits way up at an elevation of over 10,000 feet, water boils at just 90 degrees Celsius. Why on earth does the boiling point change just because you went up a mountain? Well, the answer lies in how we actually define boiling. A liquid reaches its boiling point when its internal vapor pressure increases enough to exactly match the external atmospheric pressure pushing down on it. At sea level, atmospheric pressure is around 101 kilopascals, which means water needs to hit 100 degrees to match it. But up in the mountains of Leadville, the atmosphere is thinner, so the pressure is much lower, only about 68 kilopascals. Because there's way less pressure pushing down on the liquid, it takes significantly less heat for the vapor pressure to catch up, so it boils at a lower temperature. Makes sense, right? All right, part 4, heat, energy, and phase. Let's talk about the role of enthalpy. None of these phase transitions just happen for free, of course. They require actual heat energy to occur, a concept chemists call enthalpy. Think about the 3 main transitions. We have fusion, which is melting a solid into a liquid. We have vaporization, which is turning a liquid into a gas. And we have sublimation, where a solid bypasses the liquid phase entirely and transitions straight into a gas, kind of like dry ice. By using Hess's law, we can conveniently model sublimation as a sequential 2-step process. The energy it takes to go straight from a solid to a gas is literally just the sum of the energy it takes to melt it, plus the energy it takes to boil it. It's like a neat little energy math equation. And here is the really crucial takeaway regarding the sheer amount of energy involved. To melt a solid into a liquid, you only need to partially overcome those intermolecular attractions. The molecules are still touching each other. They're just loosened up and sliding around now. But to turn a liquid into a gas through vaporization, you have to inject enough energy to completely sever those intermolecular ties, launching the molecules far apart from one another. That is exactly why the enthalpy of vaporization for any substance is always significantly higher than its enthalpy of fusion. Finally, Section 5, Mapping States of Matter. Enter the phase diagram. So we've talked a lot about temperature and pressure separately. Now let's mash them together into the ultimate cheat sheet chemists use to predict the state of matter under any possible condition. We call this a phase diagram. By plotting pressure on one axis and temperature on the other, we get this comprehensive master map. It clearly marks the exact boundaries where solid, liquid, and gas phases exist, and the lines separating these zones, those represent the phase transition equilibria we just discussed, the precise combinations of temperature and pressure where things like boiling, melting, or sublimation occur. It is an incredibly powerful visual guide that tells you exactly how a pure substance is going to behave, no matter what crazy environment you throw it into. But this leaves us with a really fascinating question to wrap up this explainer. We know what happens at normal temperatures and normal pressures, but what happens when we push temperature and pressure far beyond their normal limits, past the absolute edge of the map? We start seeing these strange hybrid states called supercritical fluids, bizarre substances that can effuse through solids like a gas but dissolve materials like a liquid. And on the flip side, under different extreme conditions, these same microscopic forces lock molecules into incredible crystalline solids, forming intricate lattice structures and perfect unit cells mapped out by X-ray crystallography. It is a wild, weird world out there at the extremes, but to fully explore those boundaries and architectures, you'll just have to keep diving deeper into the amazing world of chemistry. Thanks so much for joining me today, and keep your curiosity flowing.